All right, so we started working on vectors, and what's really important when we get to some of the more complicated applications of vectors is always to go back to this sort of like core understanding of what's going on here. And the idea is that we can use vectors to represent points, we can use vectors to represent lines, then we're going to use vectors to represent planes. But all throughout that, what we're really talking about is adding or subtracting different vectors. We'll get into multiplying later, but right now we're just talking about adding and subtracting vectors. So let's look at a point, a random point like 2 comma 3, and let's look at another point, let's say like -1 comma 5. Okay, what a lot of you have done many times in your math career is you have found a line that connects those 2 points. Okay, and what I want to show you is a way we can think about that line in terms of vectors. Okay, so here is what you do a lot of times when you're trying to find a line between 2 points. So think back to Algebra 1 skills. You think, all right, so the slope is going to be the rise and the run. So this one I think, okay, goes down 2, goes over 3, so down 2, over 3. And then you find the y-intercept, or you use point-slope form, whichever one you like more. If you did point-slope form, maybe using this point, you could say y minus 5 is -2/3 times x plus 1, or you could have used the 2 comma 3, and you would have got an equivalent equation that looks like this. Just distribute it out, and you'll see that those 2 equations are actually equivalent. Okay, you could have also solved for b and figured out that the b value is like 3 1/3 or something like that. Okay, so or 4 1/3, 4 1/3. Okay, so this is our old way of doing things. But what I want us to think about is, let's just think about this in a slightly different way. Instead of thinking of a line that connects all of our x and y points, in fact, I'll just use Desmos to type that in, y minus 3, -2/3, x minus 2. Great. Instead of thinking of it as a line that connects all the points there, I'm going to think about it as the addition of vectors that gets to any point on the line. So let me draw for you the vector 2, 3. So if I say that like vector A is equal to 2, 3, I'm writing the components in alphabetical order from top to bottom. So 2 is x, 3 is y. What that means is that's a vector that goes 2 steps to the right and 3 steps up, like that. Okay, and the vector B will be the point -1, 5, meaning it goes 1 step to the left and 5 steps up. So there's vector B. One of the really nice things about vectors is that we can pick them up and move them around. So here's vector A, here's vector B. I can actually pick up vector B and go 1 step to the left and 5 steps up. So where I would go 1 step to the left, 5 steps up. Right here, it would land at 8. And I could also pick up vector A, so this is still vector B over here, translate vector A, that goes 2 steps to the right and 3 steps up. And you'll notice that they're making this really nice parallelogram. And you'll also notice that the line goes along the diagonal of that parallelogram. So adding 2 vectors is going to make a parallelogram because you can always translate a vector around and it doesn't change what vector it is. Usually I draw my vectors starting at the origin, but you don't have to. They could start at any point. A vector just moves in the direction and the distance according to its components. Okay, so what we're really trying to do with vectors, though, is we're trying to find the vectors that go along that line, okay? And so what I want you to think about is, what would it look like if I did negative A? Well, negative A would probably just mean we make the x component negative and the y component negative. So that would just mean we're going to go down 2 and then 3 to the left. And so if we think about going from this point right here and going, sorry, what did I say? Yeah, so it goes left 2 and then 3 down. And so if I go left 2 and then 3 down, 1, 2, 3, that right there is negative a. And then we can what happens? I got myself confused. So vector b minus vector a. Oh no, yeah, this is fine. Look at vector b minus vector a. If I go from the origin to this endpoint right here, you can see that that is going to be parallel to the line that I drew in mx plus b format. Okay, so let's just go over that one more time because I confused myself for a second. So doing negative vector a is just taking the x and y components and making them both the opposite, multiplying by negative 1. If you do vector b minus vector a, I'm just doing it like a vector addition, where I'm taking negative a and sticking it on the end of vector b. And you can see that that gets me this vector down here, vector b minus vector a. And you can also see that that end result down there is parallel to the line that I'm trying to find. And because I said that we can translate vectors around, the line itself also contains the vector b minus a. Okay? So what I'm going to claim to you is that we can describe all the points on the line by using this idea of the vector b minus a. So let's think about what b minus a is. If you look at b and a, we have vector b, negative 1, 5, and vector a, 2, 3. Then subtracting the x's gets me negative 3. Subtracting the y's gets me 2. And this should look very familiar from our slope that we found earlier. It's just upside down of how you are probably used to it. When we write our mx plus b, we do rise over run. Here we've got the x on top and the y on bottom because we're just writing the components in alphabetical order. And so it's the same idea, though, that we're going 3 to the left and we're going 2 up. Or if you want, you can think about going the other way where you're going 2 down and 3 to the right. Those are going to be the same pieces. Okay, so I'm going to clear everything out just to have a little bit of space here. So what we've determined is that b minus a, vector b minus a, goes right here along the line. So that's a vector b minus a. And if I start at the origin and go right here on vector a, if I do this, vector a plus vector b minus a, I hope you agree that adding those two things together would just be getting to vector b. So what I've shown you so far is that adding the vector a and adding the difference b minus a could get us to point negative 1 comma 5. What would happen if I went vector a plus 2 copies of b minus a? Well, that would just move me one more vector along. So I would go another 3 steps left and 2 steps up, and that gets me to another point that's on the line. That point is negative 4 comma 7. So x first, y second. What would happen if I did a vector a minus 2 copies of b minus a? Well, minusing copies just means I'm going to go backwards. I'm going to go 1 and then 2. And so that gets me to negative 1, comma 8. So what I'm claiming is that every point that's on the line, every x comma y that's on the line, can be reached by starting at vector A, which is 2, 3, and adding some multiple of b minus a. And remember, b minus a was essentially looking at the slope. B minus a was negative 3 and 2, because we went 3 back, that's the negative 3, and 2 up. Okay, so that's how we get the equation of a vector line in 2 dimensions. And I hope you can see that if we do more or multiples, or if we allow k to be a fraction, or if we allow k to be an irrational number, we can reach each and every point that is on that 2-dimensional line. Now you might be asking yourself, and this is a good question, why are we doing this? And the reason we're doing this is because this sort of an equation is very easily extendable into 3 dimensions in the way that an mx plus b is not. I want you to try to think about how would you even write a y equals mx plus b in 3 dimensions? What kind of rise over run could you possibly do when there's 3 directions? How would the x and y and z all be packaged into one equation in 3 dimensions when you're trying to just write y equals mx plus b? It can't be done. But if I wanted to do a vector line between 2 3-dimensional points, like for example, let's say my points are 2, 3, 1, and then my other point is negative 1, 5, 7, well, the x components still have the same change. The y components still have the same change. And now all that's changing is my z components are changing by 6. So I can actually very easily just extend my vectors into the 3rd dimension, x, y, z, 2, 3, 1. And then let's think real carefully about this direction vector. Negative 3 came from going 2 down to negative 1. That's a change of negative 3. 3 to 5 was a change of positive 2. So 1 to 7 is a change of positive 6. Now I just wrote my equation in 3 dimensions. Okay? So that's it for this just really intro. Please remember though, when we're writing more complicated equations, it all comes back to this idea of vector addition and then adding multiples of vectors to each other.